Hey guys, welcome to your first amazing video. Today we're going to be talking about lab safety and we're going to be discussing some sort of basic laboratory techniques. I call them basic laboratory techniques because they're things that are really critical because you're going to use them a lot. Okay, and in fact, we're going to be using them throughout the duration of this class with some different types of methods that we're going to be doing. So it's good kinds of things to know. Okay, but first we're going to start out with a little bit of lab safety. Now, I know it's everybody's favorite topic, right? It's sort of like, you know, don't put things in your mouth, don't play with broken glass, things of this nature, okay? But there are some important things, okay? And I want to just make sure that we kind of go over these together. First of all, you should never be working in a lab alone, ever, 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 okay? Or unsupervised. So typically, and really for you guys, this probably isn't going to matter as much since, there's a couple of you and we're all meeting at the same time. This is kind of more relevant for situations during the normal school year when you might be coming in to make up a lab, like during a lunch period or something like that. But you always want to work with a partner, never work alone. Something happens, there's nobody there to help you, right? So that's sort of important. You want to always make sure that what you're using and what you're working with is something that you're supposed to be you're supposed to be using, okay? So you may come in any given day and there may be some pieces of equipment out or some chemicals and things like that. You don't want to start using things unless you're sure that they go with the lab and it's things that you're actually supposed to be using, okay? A lot of chemicals can be dangerous, okay? They can cause injury, they can be explosive, flammable, and some things could be dangerous that even you might not think if they're mixed with the right other types of chemicals. So just something to be careful of, okay? Don't wear open-toed shoes. This is something that's going to be really important because really you don't want to spill things on your toes. You don't want to drop sharp items on your toes, okay? It's a big no-no in the lab, so you always have to have a closed-toed shoe. Yes, that means no flip-flops. I'm sorry. I know it's Florida, and I'm making you very, very sad right now, but you will get through it, I promise. All right? No flip-flops. Safety goggles, of course, is an important one, and you're going to want to make sure that you don't have clothing that's baggy or loose-fitting, because what can happen is if you're hanging over the side of a laboratory bench doing something and you've got baggy clothing, it can snag on things like Bunsen burners, right, or even beakers full of chemicals or substances. You can knock things over, cause spills, broken glass, etc. Okay, so baggy is not good. Form fitting is good, just regular, it doesn't have to be super skin tight, right, but something that's not really baggy is what we want. And if you happen to have long hair, okay, you have to make sure that you tie it back because we don't want, again, your hair landing inside of chemicals and things like that. All right. Finally, in case of accidents and spills, always make sure that you let your instructor know, which in your case is me. So if you spill something, if something breaks, it's okay. It's not the first time it's happened. It's definitely not going to be the last time, okay? But you want to make sure that you let me know so that I can take care of it. Um, for example, I don't ever want students cleaning up broken glass. Okay, just for obvious reasons. That's something that I'll take care of if we get there. Let's cross our fingers and hope that we don't break anything, but it does happen. So I'm gonna let you guys watch this video. It's actually one of my heroes, and hopefully you like it. It's just another little bit more on lab safety. Okay. All right. That was an awesome video, right? Oh, you've got to love Hank. He's the man. All right. So now what we're going to do is we're going to talk a little bit about making solutions, okay? I have this image up here just because it shows you some of the different types of laboratory equipment that you're going to be using. Some of this stuff you should be familiar with already. Things like beakers, graduated cylinders, right? Weigh boats for measuring things, okay? All things you've used before, the stir plate. There's going to be some new stuff though, okay? And one of the things that you guys are going to get to do in this class that's going to be pretty neat is you're going to get to learn how to use some new technologies, okay? Things that actual neuroscientists use in neuroscience laboratories every day, all right? Here we have a pH meter. Now we're actually not going to be using a pH meter that looks like this. We're going to be using a simplified version because it's smaller and it's easier to maintain, and it does just about the same job, at least for what we need it to do. Here we have some pipetters. So we're going to be learning how to pipette well, right? And using these sort of more sophisticated types of pipetters. And here we actually have two devices that we're going to use to be able to quantify and measure protein, specific types of protein in a sample from tissue. Okay, this is actually a transfer apparatus, or excuse me, an electroblotting apparatus that we use to do something called SDS page, electrophoresis, and Western blotting. Okay, these are all really, really cool things that you guys will be learning about later. All right. But for now, before we can get to that, we have to actually learn how to prepare all the things that we need to do in our experiments. And any scientist, I don't care who you are, who does actually wet lab experiment type things, has to learn how to make solutions. Okay, so that's where we're going to start today. All right, now you guys should remember from your chemistry class, of course, yes, you loved it, I know you did, right? Heterogeneous versus homogeneous, okay, two different types of mixtures, and we know that a heterogeneous mixture is not uniform throughout, right? You think of things like cement, okay, is a good example of that. And then you have the homogeneous mixture, and another name for a homogeneous mixture is a solution, okay? So what we're going to be doing in here is we're going to be learning how to make solutions because we're going to be using solutions to perform different laboratory experiments, okay? So for example, one of the first things we're going to do is some histological staining. You'll learn all about what that means after a short time here, okay? But in order to do the histological staining, we're going to have to make some ethanol solutions, we're going to have to make a staining solution, and we're going to have to prepare these things, okay? So we're going to learn how to do this, all right? You can sort of disregard this part on the side, but basically it's just showing you, in case you had forgotten all about solutions because it's been so long since you took chemistry, okay? They can be different phases of matter, right? You can have a gaseous solution where you have two different types of air combining. You can actually even have a solid solution. It's something that's somewhat uncommon, right? But if you actually keep two pieces of metals pushed together tight enough for long enough, they will actually start to exchange places, some of the atoms of the different types of metals, and that will form a solution. Isn't that great to know? Yes, we don't care about that, right? Because we're going to be making liquid solutions. So everything we're going to be doing is going to be preparing solutions where we're dissolving either two liquids together, right, or a solid into a liquid, all right? And so we're going to be using solutes, so that's the thing that we are dissolving, right? The thing that we're actually adding is the solute, okay, into the solvent. The solvent is the medium that we're actually diffusing into, right? So example, I'm going to make some salt water, right, because it just tastes so great, or maybe I'm sick and I need to gargle it or something like that, right? So I'm going to make some salt water. My sodium chloride, my salt, is going to be my solute, okay? Sodium chloride will be the solute. The solvent is going to be my water, okay? In the laboratory, we're going to use distilled, deionized water because we like it to be nice and pure, right? When we're making things, we know that ions can affect the properties. They can affect the structure of molecules and different things like that. So we want to make sure that we're using the best water. So we're going to be using a very special type, all right? Now we have different types. Sometimes we think about a solution being really concentrated, okay, or being very dilute. All right. Now, concentration is everything, and we're going to be spending a lot of time talking about this in this particular section when we're learning how to do the math, okay? But essentially, concentrated means that we have a lot of solute, right? And dilute means that we have a little bit of solute. So you can imagine if you had a solution, and let's just use salt water as our example, right? And as a sodium chloride solution, and let's say it was very dilute, it's probably something like 0.0001% sodium chloride, okay? So that means you just got a little teeny bit amount of sodium chloride in it, all right? Now, if it's concentrated, that means that we have a lot, okay? So a concentrated solution contains a lot of different solute. Well, actually a lot of solute, period, right? So it's concentrated. The problem with using these words in their general sense, concentrated versus dilute, is that we don't really have any reasonable appreciation for how much or how little, as it can turn out, right? All we know is that we have either a lot or a little, but that's not particularly helpful to us, particularly not when we're doing science, where we have to be very precise, and we're doing experiments where we have to have specific amounts of all of our chemicals or reagents. Okay, it's another word we're going to use to describe some of the different chemicals we're using. Oftentimes we call them reagents. Okay, so we're going to want a precise method of actually measuring this stuff. All right, so essentially, solution forming, okay, there's different factors that affect this. Before we get to doing the math and figuring out how to actually make these, I kind of just wanted to review this for a moment, right? Because we're going to be doing some of this when we're making our solutions, okay? Sometimes you might have a compound or a substance, a reagent, a chemical, right, that is less soluble, okay? Or you might be trying to dissolve a lot of it into the water. And sometimes things tend to dissolve a little bit slower, and you have to give them a little bit of help. Okay, so there's different ways that we can actually affect, okay, the formation of a solution, how quickly it forms, right? And one of them is by stirring or agitating it. So we're going to be using especially, stir plates, basically is what they're called, with magnetic stir bars to actually kind of speed up the process a little bit. This is also going to increase surface area of the solute sometimes, because you might have chunks that sort of congregate when you have a bottle sitting around for a while. They kind of tend to stick together, and so agitating and stirring actually will kind of help to separate some of those chunks. It increases the surface area, right? And we know that in order for something to dissolve, we got to get all those different particles in contact with each other, right? All the particles of the solute have to come into contact with the particles of the solvent and do all these things like this, right? So what better way to do it than to spin it real fast and sometimes heat it up, right? So if we increase temperature, we're increasing kinetic energy. If you remember, once again, from our lovely chemistry, that kinetic energy, all right, is essentially what we're measuring when we measure temperature. So the faster they're moving, the more they're going to be spreading around, the more collisions there's going to be, and the more that they're going to dissolve, okay? Particle size we won't really have to worry about too much here, because we're essentially going to be using things that dissolve anyway. All right. So we're going to be talking about solubility. Most of the things that we're going to be using, we already know that they're soluble, so this isn't really going to be an issue for us, but it's just good to kind of review it. Okay. That solubility does, in fact, depend on several factors. All right. One is how much you have. Right. So you can only, the solubility of something, a lot of times we talk about it per 100 grams of water. Okay. So if something is very soluble, that means that you can dissolve a lot of it, right? If it's not as soluble, that means you can't dissolve as much of it into a given volume of water. And usually we reflect this, like I said, in 100 grams, okay? And it is temperature dependent. Things tend to dissolve better when you heat them up. So occasionally we might have to heat something up to get it to go into solution. All right. So water solubility, yes, we're using water. So all the solutions that we're making, we're going to be calling them aqueous solutions. Okay, that means that they are solutions that are composed mostly of water. Okay, water is our solvent. So that's what we're going to be using. And we kind of remember the rules, right? That water will dissolve most ionic things, okay, and polar substances. You remember from your chemistry class, when something's asymmetric and it has an uneven distribution of charges on the ends, we can say that it's polar, okay? So polar things like water, water is also polar, right? So like dissolves like kind of deal. So the reason why this stuff is important to think about, okay, outside of this class, and just thinking about solubility and what types of things will dissolve in water and why we care if something dissolves in water. Well, if you think about it from the standpoint of medicine, okay, what are we often trying to do? Well, we're often trying to come up with new drugs, okay, or new treatments to treat a certain type of ailment or disorder, right, or injury. Okay, and particularly in neuroscience, this tends to be a big problem. Okay, because one of the things that we have to be able to battle past in neuroscience when we're actually giving a drug is something called the blood-brain barrier. And we're going to talk about that a little bit more later, so you don't have to worry about that too much now. But the idea is that we actually have even a separate barrier between the blood and the brain that we have to be able to get through, okay? Now we know that if you look at a certain types of molecules, okay, they might have more polar regions on them, right? So they might be more soluble in water, whereas other compounds might have more nonpolar moieties, okay, or regions on them. And if they have more nonpolar regions, they're not going to be as soluble in water, okay? So what that means for us, okay, is that when we're making a good drug, okay, when a neuroscientist is trying to come up with a drug that's going to be effective, they have to think about some factors, right? One of them is actually obviously the activity, right? So how well is the drug actually going to work? And this sort of funny little binding stuff to the target here, we're going to go through all of that, so don't worry. But solubility, okay, is a big factor. And what this is basically the question that we need to ask ourselves when we're making a drug like this, okay, is it going to be absorbed well enough by the body to actually be effective? Because you remember, you might take a drug, right? If I take a pill, I swallow it, it's going to go into my stomach down here, right? And then it's going to get digested by some enzymes. The drug is going to get released. Now the drug still has to get absorbed into my bloodstream. And it still has to end up going to the site. So let's say that I'm taking a pill because I have a headache, right? Well, this drug needs to get from the stomach all the way up here, okay, to be able to exert its effect and relieve my pain in my head, okay? So the ability for something to be soluble and be able to get into the blood and move around the body is really important, okay? And so sometimes, a lot of times what they have to do is they have to change the structure of the molecules and add different things onto them to make them more polar or less polar so that they actually get to the site where we want them to go, okay? It's kind of neat stuff. This is just a little picture that kind of shows what I was just describing. This is, you don't have to worry about for those of you guys who are interested. Whenever you give a drug, you usually measure, okay, the plasma concentration. So what that tells you is how much of it is present in your blood, okay? So if you have a high plasma concentration, part of your blood is actually made of plasma. That tells you that a lot of it has gotten into your blood, okay? If you have a low plasma concentration, that means that not much of it has absorbed, okay? So this is one of the ways that scientists can tell experimentally, once they give something, how effectively it's actually absorbing and getting into the system. All right, so in the next part, we're going to deal with preparing solutions.